All right, chapter 13. So we have an opportunity now to learn some really cool stuff about solutions, mixtures. And remember, solutions are mixtures, right?
Yeah, I get that.
Let's go over a little bit of vocabulary to make sure we're on the same page. What are the two different components in a solution?
What do you mean the two?
Well, the two different kinds of components. Remember, there's the solute.
Oh, yeah, the solute and the solvent.
Very good, the solute and the solvent. And I guess the solvent is the one that's in higher concentration.
Yeah, okay, that makes sense.
All right. And we've talked a little bit about how to determine the concentration. You know, everybody should know how to determine the concentration of a solute in a solution. All right. And in one of the labs, if you were lucky enough to have the in-person lab or had some experience identifying concentrations in different, expressed different ways, we'll get into that in this class. But molarity, do you remember what molarity means?
Yeah, that's like moles per liter.
Moles what per liter?
Moles of solute per liter of solvent.
No, not moles of solute per liter of solvent, but moles of solute per liter of what?
Solution?
That's right. Moles of solute per liter of solution. Okay? Good. So those are the kinds of things we're going to be talking about in this chapter. All right? Here's a little bit of a review about this phrase, like dissolves like. Do you remember what that means?
That means like if you have one compound that has dipole-dipole interactions and another compound that has dipole-dipole interactions, the two of them would be able to mix together well.
Okay, very good. So, for example, if I had something like water and oil, why don't they mix together very well?
Water has dipole-dipole, actually hydrogen bonding, right?
That's right.
What does oil have?
Well, oil is pretty much just long chains of carbon. I don't know if that helps you. Let me draw out a little example here. So it's just carbon after carbon after carbon after carbon after carbon, all right? Oil actually looks, we have a glycerol, whoops, that's a carbon there, glycerol head, and we have 3 of these chains of, and I forgot in here, a double bonded oxygen on all those, but we have 3 long chains of hydrophobic material. Okay, and this is actually what you call a triglyceride, all right? So this is a main component in oil. So what do you think? What kind of intermolecular interactions could this kind of compound make?
Well, there's some oxygens in it, right?
Yeah, there's a little bit of oxygens here, but there's no hydrogens, so you're not going to get hydrogen bonding, maybe a tiny bit of dipole here, but I've only drawn 1, 2, 3, 4, 5 here, and these really, and I'll draw them like this to save myself some time. They go on to, you know, in the 10s and 20s in terms of carbon lengths.
So all those is just London forces, dispersion forces.
That's right. That's right. And so that's why water, which has hydrogen bonding capabilities, and oil, which only has really dispersion capabilities, don't mix together well. Okay? Very good. So when you have similar types of intermolecular forces that a molecule can interact with its neighbor with, then those types of compounds, if they're similar types, will be able to mix together. All right? So here's an example of a compound, ethanol, and how even though it's not exactly the same as water, they can mix together well. And that's because ethanol can undergo hydrogen bondings, 2 carbons with 5 hydrogens around those carbons there, but there's an OH bond here, and that can undergo hydrogen bonding with the water molecules, therefore the 2 of them can dissolve together. And the word we talked about was miscible. If you take 2 liquids and they combine together and they mix, then miscible is the word we use. Okay. Immiscible liquids, immiscible. Now see here, this is an example of 2 liquids that do not combine well. And you can see one's on the bottom and one's on top here. all right? And they're not different colors, and so it's kind of hard to tell. But why aren't these two mixing well? Well, because one of them is ethanol, and one of them is benzene, all right? So ethanol, what kind of intermolecular interactions can ethanol undertake with neighboring molecules?
Hydrogen bonding.
That's right, OH group there. We see that there's a possibility for hydrogen bonding with neighboring molecules. How about benzene here?
Well, so it just looks like it can just dispersion forces, right? No oxygens, very symmetrical.
That's right, very good. Okay, so that makes these two compounds, which are both liquids, immiscible. All right, so which of the following would you expect to be miscible with this water molecule here?
Let's see, acetic acid, that looks like it would be miscible, right? Because it has some oxygens with a hydrogen on it, right? Is that what that is?
That's right, this is an oxygen-hydrogen OH hydroxyl group here. And so this oxygen and hydrogen can hydrogen bond with that water molecule.
Carbon disulfide, sorry. I don't know much about that.
Well, it looks like it's linear. Should we draw it ourselves?
Maybe we should draw it.
So if we have carbon and 2 sulfurs, then that's going to be a total of 4 plus 6 plus 6 valence electrons, right? 4 for carbon, 6 for sulfur, 6 for the other sulfur. So 16 valence electrons, carbon and then sulfur. 1, 2, 3, 4. So we have 12 more valence electrons. 1, 2, 3, 4. And 12 more left here. 5, 6, 7, 8, 9, 10, 11, 12. I think we can see pretty quickly here that we're going to have to move some over here and move some over here. So it looks like it's going to end up being similar to carbon dioxide, but with sulfurs, right? Okay, so it is linear. Is a carbon-sulfur bond polar?
I can't remember. Can I look at the periodic table?
Yeah, we can look at the periodic table, but we should remember that even though, let's see, where's my periodic table? Even though, so here, let's look at the periodic table here. What are what are you looking for?
Electronegativity.
That's right, electronegativity. So here's carbon, here's sulfur, all right? What are our 3 most electronegative?
Nitrogen, oxygen, and fluorine.
Very good. So carbon is less electronegative than nitrogen, and sulfur is less electronegative than oxygen. But even if there was some polarity here, it's not going to be much because they're pretty close in terms of their distance from these 3 hogs. And also, we have a symmetric molecule, right?
Oh, yeah. Okay, so it's not polar, so it's not going to be able to dissolve in water, be miscible with water.
Very good. How about ammonia?
Is that symmetrical?
That's a good question. That blue, you know what the blue is?
That's nitrogen, right?
Yeah, we've talked a little bit about ammonia before, so I don't know if you remember. But if we were to draw this out, NH3 is the chemical formula, we'd remember that there is a set of lone pair electrons on top. And so this is not a symmetrical compound. It's drawn like this because we're kind of looking at it at the top. But what would that do? What would that mean to you?
Well, it would mean that the nitrogen-hydrogen bonds are polar, so it would dissolve in water.
Okay, it would be miscible with water. Very good. Excellent. Okay, let's try to answer this question now with these types of descriptions of compounds. Now, we're trying to get more familiar with what this sort of thing means when we see this. Are you familiar? Are you comfortable with this?
I think I'm getting the hang of the first one at least. We got 4 carbons, 3 on the first, 2 on the second, 2 on the third, and then 3 hydrogens, on the last.
That's right. So we got carbon, 4 of them bound together, 3 hydrogens, 2 hydrogens, 2 hydrogens, and 3 hydrogens. Okay? So, what kind of intermolecular interactions?
Just dispersion forces, London forces.
That's right. So, not going to be miscible with water, right?
Right.
How about C6H6?
I'm not sure about that one.
Well, you actually do know, but we're not familiar with what this means. So when we see C6H6, what this means is 6 carbons in a circle like this, a ring, and then 6 hydrogens bound to those carbons. Now, we know that each carbon has to have 4 bonds, and so we can distribute double bonds until every carbon has 4 bonds. But have we seen this before?
Yeah, we just saw that on the previous one.
That's right. Right here, right? Benzene. So what did we say about that?
Not miscible with water.
All right, now how about this one? CH3CO2H. How is that going to look?
One carbon with 3 hydrogens, and then it's attached to a carbon, and then 2 oxygens coming off there, and then I guess the hydrogen's coming off one of the oxygens.
That's right. And when we see that there's not a double bond, or not 4 bonds to this carbon, we have to make a double bond to one of these oxygens. All right, I'll throw in the lone pairs so that you can be a little more comfortable with what we're seeing there.
So that is going to be miscible with water.
That's right. That's our acetic acid again that we saw before. So we kind of want to become familiar with this.
How do we know C6H6 is in a ring?
Well, that's a good question. And it doesn't really need to be in a ring for us to know the answer to that question. But that is generally what's being referred to when we talk about C6H6. Let's see, 1, C2, 3, 4, 1, 2, 3, 4, 5, 6. So this compound here would have how many hydrogens? 1, 2, 3, 4, 5, 6, 7, 8. So we need to have a triple bond in here to get rid of there. So you could have chemical formula C6H6, carbon with a triple bond, carbon with a double bond, carbon with a double bond, 1, 2, 3, 4, 5, 6, and then it would have 2 hydrogens here, 1, 2, 3, so we'd have to have a 4th hydrogen there. These both have 4. This would have to have a hydrogen there, hydrogen there, hydrogen there. So it's 1, 2, 3, 4, 5, 6. So any compound that you could draw that would have C6H6 in it would still be just London dispersion forces because it's just carbon and hydrogens.
All right, I got it.
Okay, very good. A little bit of a review on how we determine whether compounds have similar or different intermolecular forces, and that's a good place to start. Good job.